Okay. So a big part of every that is going to struggle with, a big part of its system is being able to get the oil back. And this is specifically an issue with shell and tube flooded styles of evaporators or hybrid falling film. And I'll show those in a minute. But um, with a DX falling film, where the refrigerant is inside the tubes or a brace plate, systems like that, based off of their design, we have a much easier time getting that oil to return. And a lot of our oil return at that point is just purely based off of our velocity in the system. So as long as we maintain a minimum amount of velocity in the flow of the refrigerant, we can carry that oil back into our suction line and get it back into our compressor, um, and our oil reservoirs, whatever we have, whether it's integrated into the compressor or an oil separator, whatever it is. We're able to get that back as the way that we need to, so that we can maintain proper oil levels. So if you've got in those types of systems with a shell and tube DX or a brace plate, something like that, tube and tube, if you're having issues with oil stacking and you're not getting all that oil come back, which you'll also, not only will you see it in low oil levels in general and inside your reservoirs, but you'll also see it in your approach values. Your approach values are going to run way higher, which aka your saturation temperature is going to be a lot lower uh, than it would normally be for that particular machine, running normally. So these are these are the factors uh, we have to take into account of the application itself. And with an eductor, why do we not see eductors implemented on these other designs? Well, because it does come back to, if we are operating correctly and we have proper velocity, the refrigerant's speed through the system and the energy that it's carrying is able to pick up the oil uh, droplets as it's moving through and carry them all the way through the system. But when we move into these other types of heat exchangers, the our velocity slows down a lot, and we don't have that same carrying ability. Our ability to retrieve that oil back into our compressor isn't the same. And so uh, we have to have some kind of device that can come alongside our system and actually help that oil get back where it needs to go. But that also means that it needs to be online. And which this is also true across any system. So whether it's a shell and tube DX or whether it's a flooded shell and tube, you're still, for the oil to get recovered without doing it manually, which is a pain in the butt process. Um, you have to be online in an operation for that to work. So looking at a hybrid falling film, hang on. An example of this YK shows us a hybrid falling film. So this falling film, without just going full blown into this, we've part of our refrigerant stream is being sent through a distribution rail. So it comes through our liquid line, hits our metering device, and hits a rail to then distribute that refrigerant over the whole length of the evaporator. And there's this spray system that mists that refrigerant over our tubes. And so a good portion of our tubes are just getting misted on them, and they're not submerged in the refrigerant. And being a hybrid, if this was a true falling film, then the entire section of tubes would strictly be getting the misting, and just a small amount of liquid might be accumulating in the bottom. But typically, with a true falling film, you will have no or next to no standing liquid refrigerant in the evaporator at all, which, to do that at the same tonnages, requires a lot more evaporator to move the same amount of heat. And the benefits of a hybrid falling film is part of the evaporator is a flooded design in its nature. So part of we spray enough to get a lot of heat transfer on the upper tubes, but then the lower tubes that are fully submerged get maximum heat transfer because water in the tubes is able to make a lot more surface contact time with liquid refrigerant to cool it down. And the whole reason we've even started using this is so that we have better efficiency, or I'm sorry, let me rephrase that. We have better refrigerant charge. We get the same basic efficiency for the same basic footprint. So the size of our chiller doesn't have to change a whole lot. It may be marginally larger. We maintain the same relative efficiency values, but we reduce our total refrigerant charge dramatically, like heavily reduce the total charge required for a hybrid system. And there's this set of baffleting in here that prevents our spray rails from being able to spray directly into our suction side of our chiller, which would be really bad. Now, these hybrid falling films are used in more than just the centrifugal application. These are also used in air-cooled applications as well as flooded systems. So looking at a flooded design, this is also a YK, but a much older style of one with a flooded evaporator. So our refrigerant is inputted here into the bottom, and we're fully submerging all of the tubes in liquid refrigerant, and then they will boil off. Now we also have an eliminator that helps even out the refrigerant pool across the whole evaporator, but it also helps prevent or eliminate droplets as the refrigerant is boiling off. Those droplets of liquid refrigerant will hit this eliminator, or this mesh screen is what it is, and allow those to stop and get vaporized before they get to move up into the compressor. Because any of our compressors, whether it be a centrifugal or a screw, whatever chiller is using this, none of them handle liquid refrigerant into the compressor very well at all. And we want to minimize that as much as possible. So you'll have these screens in here to help ensure that that doesn't happen. But in either of these designs, we cannot return oil up our suction line in the same way that we can with a DX. So the DX, the refrigerants in the tubes, the water is on the shell side. But in a flooded or hybrid falling film, our refrigerants on the outside here. And because of this refrigerant cycle, the oil that does make it into the condenser is able to flow down, fall, drop to the bottom, or even if this was an air cooled, the same basic process. We're going to come down an air cooled coil, and the discharge gas goes into the top of the coil, liquid line flows out the bottom. So there's a very natural, just gravity fed type system that's able to move that. And then uh, that oil that does get into the condenser will flow out, and it will make its way to the evaporator, whether it be a water cooled or air cooled design. But then once we get to the evaporator and we've got these flooded or hybrid designs, that oil and there's not enough velocity coming off of this oil to get that oil to properly return to our compressor. Now, depending on our compressor, we may or may not even want that oil to get there to begin with. So with a centrifugal, we don't want that oil to be able to get to the impeller to begin with. We want this to be as clean of a refrigerant as possible. With a screw compressor, on the other hand, it's okay if we do get that oil up into our suction line, and that's an okay process. That's a normal process. Screws require heavy amounts of oil in order to keep them in safe operation or just make them function to begin with. Either way, despite the style of compressor, this evaporator is not conducive for that oil return process. So we implement a device known as a eductor. Now, these are also referred to as jet pumps. There's a third name I've heard them like a Petrelli or something along those lines. So there's a few different names for the overall design of this, and how it gets used and implemented. Jet pump is the most common term I've heard used for these outside of chillers. Just in the chiller world, though, you will read in manufacturer's literature, and you'll hear these terminology used for an eductor. It is eductor, eductor. Your spelling correct tools will want to say educator every time, so just be forewarned. Anyway, what's happening here is we've got a device that is going to take some high pressure discharge gas and sends it into this nozzle assembly. Now, because this is flowing at a high pressure with high velocity and then pushes through this nozzle assembly, we create a siphoning effect. So in the siphon, it's very similar to just what a straw is doing, or just any kind of siphon you can get going. And that siphoning effect allows us to draw some oil latent refrigerant. So we want refrigerant has a high concentration of oil in it, or potentially a high concentration of oil, so that we can then we can then inject that into this pump on the suction port of it, so that it will then push that oil latent refrigerant into a vapor state back to typically our suction line or our oil reservoir, depending on the compressor and the design of the system. So these can be located in a number of different places. They can look in a few different like orientations and styles. They don't all look the same, and they don't all look like this. This is just one example. This particular example is out of a YVAA air-cooled screw chiller. So you'll see a little bit of variation there, but the overall fundamental like internal concepts of what's happening here is true, and the fundamental engineering of what a jet pump or a eductor is doing doesn't change based off of the system. It's just where it's located and exactly where it sends the output to is what really changes the most. So part of what we have to keep in mind is the oil, because oil is lighter than refrigerant, the oil will it'll concentrate here at the top, typically, of that refrigerant. Now, depending on your type of evaporator and where things are set up, um, where that refrigerant line is can fluctuate heavily depending on your particular machine. So where these the oil recovery ports for the eductor are located on these machines can vary quite heavily. They could be far more towards the bottom. They could be up more of a midpoint. They could be at somewhere in between there. They will be located in a few different locations, just depending on that specific chiller's evaporator and where the manufacturer expects that refrigerant level to be. But these eductor ports are designed to operate just below the top level of what that eductor was meant to draw in. And that's where the majority of our oil is expected to accumulate during operation. And just the bubbling action, it's going to bubble up and get to the top up here. Uh, and if you have a sight glass, one of the ways to know if you're heavily oil latent is by how much foaming action do you have in there. The more oil you have in a system, the more foaming action you will have at that top layer of boiling. Um, and it'll also, many times, it'll have like a yellowish tint or orange tint to that foaming. It won't be, just white. Which refrigerant boiling off, especially at high load and creating like a little bit of a boil film, is normal to some degree. It's usually not very heavy or excessive, though. So when you start to see really heavy foaming during normal operation, and especially if it has a color tint, then that's when you should start being concerned about um, your oil stacking a bit heavy in the evaporator, and whether or not your reductor may be functioning properly, or if you're having other kind of migration issues or anything of that nature. But in terms of where the line is tapped into the evaporator, will that's what that's dependent upon, is where is that liquid level expected to be, and where that refrigerant is going to have the highest concentration of liquid refrigerant with oil in it. Any questions on that so far? Yes, that is right. And so, go ahead. Yeah. Well, and that's one reason why on some of these evaporators, the you'll see some of these eductor ports are very low down towards the bottom of the evaporator. Not all of them, but some of them. Well, and that goes back to typically when I see that, they're usually the hybrid style or design. Uh, One example, and that's not using an eductor, but a RTHD as an example. That's a hybrid falling film evaporator, but it actually has its oil recovery system that's using a gas pump. So it's a different style of recovery, but it's right at the bottom of the barrel. And part of that is because that chiller runs such a low liquid level. I mean, the liquid level sensor, which is what controls the EEVs on that, are right at the bottom of the evaporator. I mean, it doesn't have a whole lot of liquid refrigerant in the evaporator. Is part of my point. Um, and so they have uh, the oil recovery intake right there at the bottom because, well, for the most part, there's not much refrigerant there to begin with. But as the refrigerant begins to stack higher and higher in the evaporator, then we need to have that recovery line adjusted accordingly so that um, we don't want to risk being over that refrigerant level, but we want to be just under the top side of it so that we are getting that mixture that we're looking for. So just to give a quick recap here, we have discharge gas coming in to this port here, and then that goes through this nozzle assembly, which then creates a type of siphoning effect, which draws in uh, liquid, oil latent liquid refrigerant. And then from there, one of the other benefits of that hot gas is it also helps vaporize that liquid refrigerant because with any system, like we don't want to, whether we're going back to our oil reservoir or whether we're going to the suction of our compressor, we don't want to hit it with liquid refrigerant, which is part of what would happen here. So part of that hot gas is it helps us vaporize that liquid refrigerant as it moves out into wherever we want that oil to be. And that's also where, like, this nozzle is our pressure separation as well, so that this isn't just a hot gas bypass. So when we're flowing through here, because we've got this nozzle and there is a pressure separation happening, that is preventing this from just hot gas bypassing directly into our suction or our oil tank, which is going to create a whole nother slew of issues. So just bear that in mind. But just from a overall, at the basic levels, this is what the internals are trying to accomplish of this eductor system. Now let's go look at a actual recovery circuit and see what this looks like. So we're going to start off. I've got 3 different examples I want to go over. The first one being a YVAA. Um, this is one that I get a lot of questions on. A lot of people are very confused with it. And it's also where, when you get into the larger water cooled side of the world, eductors are very commonly used, or oil recovery system of some kind is used very heavily. But historically, with with air cooled systems, um, they're not. We don't use falling film or flooded evaporators as often. We are starting to now, and a YVAA does do that. Typically, they will either be a brace plate or there'll be a DX a shell and tube DX evaporator, which we don't need an oil recovery system with that, if everything is functioning properly. So my point being, this gets confusing as you start getting more advanced into the air-cooled side now, because these eductors are starting to be implemented there because of the types of evaporators we have. So with a YVAA, we have it's a hybrid falling film evaporator. And again, one of the main reasons we know that is we have a sight glass and we maintain a level of liquid refrigerant in the evaporator. So while the manuals may reference a falling film evaporator specifically, they're just leaving out the hybrids, point there. I just want to make that clarification. When it says falling film, it's a hybrid style of falling film, not a traditional falling film. Either way, our refrigerant gets injected into the top of the evaporator. There is a spray rail system in here that sprays this refrigerant over the tube assembly, and then our suction line also comes off the top of the evaporator as well. So we don't have any lines or connections here at the bottom of the evaporator except for our oil recovery tap for our eductor. So the way these are piped, I'm gonna start off over here on the high pressure side. Now I do want to make one clarification with this schematic. This particular schematic is referencing the early versions of the YVAA, where the eductor hot gas line got tied in at the compressor discharge. They stopped doing this because, one, this refrigerant here is already very oil latent, because it hadn't even made it to the oil separator yet. But also the vibration of this line right here at the compressor, they had a lot of issues with it blowing out and fracturing or cracking, dumping the charge. So one of the modifications you'll see with a YVAA, if you're comparing this particular schematic, the the field procedure was to move that hot gas line over here to the outlet of our separator, and that stopped the vibration issues with cracking the line and the heat issues, as well as we got far less oil latent gas going over to there, so that it didn't impede our ability to draw in oil latent liquid from our evaporator. So anyway, in a new system, we're coming off from over here. That's my point. Regardless, we come off of our discharge side and we're a superheated hot gas refrigerant, a high pressure hot gas. And then we come into our eductor block. Now, this eductor block is exactly what I showed a minute ago via that diagram. And then we've got our oil recovery port coming off of the evaporator. And this evaporator maintains a really low level of liquid. It's not very much. So this eductor line is actually really low on the evaporator. But we're pulling that oil latent liquid refrigerant off, And this particular machine flows that liquid through a filter dryer. So you've actually got two filter dryers in this particular machine. You've got one for that liquid refrigerant off the bottom of the evap for the oil recovery. We've also got another one on the liquid line coming out of the condenser. Um, Either way, the two gases, or the liquid refrigerant and the hot gas, mix in here inside the eductor, and the Venturi effect takes place where we're siphoning off and creating that draw. And this is where we enter into a it's a oil latent suction gas that's more of a medium pressure. Okay, so this isn't a true low pressure at this point. It's a medium pressure flowing through here, and that's part of just the pressure equalizing process of that, low pressure liquid refrigerant mixing with the high pressure vapor gives us a medium pressure return coming back into our suction line. This particular machine just returns it to the suction. We've got a screw compressor, so that oil coming back through our suction is expected and is just part of our process. There's nothing wrong with that on this particular compressor. We just don't want the liquid refrigerant to get back to the compressor, but our oil returning isn't going to cause us any issues. Any questions on this particular setup, which for like they're not doing anything here that most other people aren't doing, maybe in just slightly different piping layouts. Okay. So let's move into a CVH. So this will be your CVH system. Now this schematic's a little complicated, and I do plan on creating some graphics that help separate these systems better. Either way, what we're focused on is the oil recovery side of this system. So instead of being a centrifugal, we don't want that oil to make it back to the compressor at all. That is not a good thing for this compressor. Those small droplets of oil turn into basically buckshot and blast our aluminum impellers, and they don't appreciate it. So we have an oil tank or an oil reservoir that is separate from the compressor. We don't have an oil separator or anything like that, so it's a very different design from the screw system. But we have our eductor right here at the top of the tank to the side. And if you didn't know this, most of the time they're insulated. You'll have this little canister thing sitting on the side of your um, oil tank, and that's a filter dryer. So this is actually a filter dryer, just like what we were doing in the YVAA example over here, except we're some of these I've actually seen are just like flared liquid line dryers being used. Specifically the larger ones, are this kind of canister style. They look different, but they don't look like a liquid line filter would look. They're a different style of dryer. Either way, in the other setup, we had three lines tied in. But if you look closely at this eductor block, we have actually four. So we've got our hot gas inlet from the condenser up here. So we're coming off that tap, coming off the top of the condenser, and then flowing into the eductor. We've got two lines right here, and then our fourth being the injection port going into our tank or our reservoir. So we're actually trying to recover oil from two different locations simultaneously with this particular setup. One of them, the most straightforward one, is coming off of the evaporator. So this has a angle shutoff valve, as a little service valve here on the side of the evaporator, and this chart actually depicts it really low on the evaporator. Most of them I've seen are up a little bit higher. They're not quite that low, and these are flooded. These CVHs are flooded machines, so The liquid refrigerant gets inputted into the bottom of the evaporator instead of coming into the top. And there's a distribution rail in the bottom of the evap. We can see that here in this example. There's this rail assembly here at the bottom, and that distributes this. This comes into a single point and then hits this rail and it gets distributed across the length of the evaporator. That helps us maintain a uh, proper flow and efficiency across the whole evaporator. And that's what you see here. So this is that inlet port for the evaporator. Now, uh, that being the case, this again, this can vary in its location. So just my point is, be cautious in some of these graphics that it shows it like right here at the bottom. That's not always the case. A lot of times they'll be kind of more up here towards the midpoint, which is about where, just a little bit above this flange. For these CVHs, they actually run a pretty low liquid level compared to the size of the evaporator. So you may have your liquid level right up here. So right about there, it's pretty common to see that. Regardless, we're going to go through this valve and then up, and we're going to get drawn into our filter assembly and then through that and into our eductor block. And the same science is happening here. We're taking hot gas refrigerant, high pressure refrigerant, and then we're injecting it into this port. This nozzle assembly in here is going to create a Venturi siphoning effect. That Venturi effect is going to cause a draw on these others while also flashing off any liquid that exists, liquid refrigerant, and then we get our oil directly back into our tank. In this particular example, we've also got a line, so if we trace this up, right there, coming across and up, right here at our nose cone, or the suction in bell of the compressor, we've got a tap right here at the bottom. And the reason this is here is so that if for any reason any oil, whether it be from the bearings or from the suction, wherever it's coming from, uh, or not, I guess probably not from the bearings, I shouldn't say that, but any oil that does make it up the suction line, it'll hit our guide vanes in here and hopefully collect down here at the bottom of the nose before it actually is able to make it into the impellers. That is our best case scenario. So with that, we have this little chamber down here that is for that oil collection, and we're also siphoning off. Now, all this is suction gas though, so we're not drawing in uh, liquid refrigerant here. We're drawing in a oil latent suction gas through this line that will then get siphoned into the eductor and then injected back into our oil tank. And between the two, we're able to get whatever oil may collect in the system that we need to return back into our oil tank. Now, one of the other things we need to think about is if we're injecting refrigerant into here, uh, and this is medium, like the refrigerant pressure coming into here is a medium pressure refrigerant. We need to have um, we need to get rid of that vapor. So all that vapor refrigerant that collects in here needs to go somewhere. It can't stay, and it can't stay trapped. So what we do is we have these vents. Now, some of this is going to depend on the generation of the machine as to whether or not you have an oil separator or just which vintage you have and how many vent lines there are. So, and just even where that vent line returns back to. Some of the older machines, they did something different with a solenoid valve. So, um, the point is, we have a vapor vent that goes and draws back into the suction side or the evaporator side of our system in order to take all the vapor that gets collected into our tank and distribute that out somewhere else in the system. Or I say somewhere else. It just gets that vapor pressure drawn off so that we don't allow too much of it to stack in here, which is going to inhibit our ability to not only move the oil, but also uh, to get the oil recovery process to work properly. And that's where with our YVAA style, this wasn't an issue because we recovered back to our suction line. So the compressor was constantly pulling on this. But when we move into a tank design like this, we need to have the ability um, to pull that vapor off and have a vent somewhere, so where we don't cause that vapor to stack, and then we build refrigerant pressure in here that we don't want to be there. Now in this particular series, it's the vent comes up here on this particular line, and then hits our oil separator, um, and then that oil separator vents out back into our evaporator. So this oil separator is also processing our thrust bearing oil and our journal bearing oil coming off the motor and the compressor. So those are processing through this same port, separates the oil out, lets it fall back to the tank, and then that same vent takes whatever refrigerant got involved in the oil lubrication process and makes sure that it can vent out properly. So it's just a way of trying to control how much refrigerant we allow into our tank assembly, um, and what kind of pressures we maintain here. So, because a big part of how we control our oil pump is based off of pressure differential. So, if we're allowing this tank to build pressure, then we're going to cause differential issues with our pump being able to keep the compressor lubricated as well. So, all of this is correlated into each other. So, yeah, this eductor system is sending refrigerant directly into our tank assembly, and then we have a means of managing that refrigerant getting in there and sending it somewhere else. Now, it is important to note, and I'll pause here to make this statement. Um, this does depend on the machine, but a lot of machines, these valves on the evaporators, these are not just they're not there for just strictly isolation. They're actually there as a field calibration device. And you'll see this on some of the air cooled. So another air cooled that uses eductors would be the AVX by Dunham Bush is another one. They have this valve and this train valve here as well. You know, when you read the specifications in the manual, these are not meant to be just full open. Um, actually what you could end up doing is you end up sending too much liquid refrigerant through this line to the eductor, and we cannot properly convert that to the vapor that we need to from the hot gas process. When we overload our eductor, and then we run the risk of sending liquid, whether into our tank, which is not a good thing. We don't want liquid refrigerant getting in here, or we run the risk of, if it's a like that Dunham Bush as an example, we start to send liquid into our compressor. That's what the oil line returns back into, or returns to the suction, which is where it hits the suction line is right next to the compressor, so it doesn't have far to go. So the point is, we actually need to be careful with these valves, and that we're tuning them properly, and we're not opening them too far. So, like what Train suggests, it's from fully closed. They should be anywhere from, what is it, a quarter of a turn to 2 turns open. So most of the time you'll go 1 to 2 full turns, but no more than 2 turns. So one turn being a complete 360-degree rotation of the stem of the valve. So no more than 2 turns out on this line. Anything more than that, uh, then you will start to overfeed this line, and you're going to cause issues with your eductor system and your oil tank being able to maintain properly. So those are things that it's meant for us to calibrate in the field. It does not come from the factory pre-calibrated. It's one of your startup procedure checks you need to do, is verifying that these valves are open, because most of the time they'll ship closed, and we've got to open this up and then make sure it's set correctly, depending on our machine. And this is true across the board. This is not a Train or Dunham Bush thing. Many machines will have this setup. Now there are some that they don't. Okay, there are some out there that just you open the valve and the chiller will regulate it in a different way on its own. But you've got to be cautious as to which ones do or don't, and make sure that you're setting it correctly. Now, um, set them to delta pressure. Uh, I'm not familiar with doing it via delta pressure across them because typically we don't have a pressure tap necessarily to set it here. We do it based off of either a predetermined flow or um, we do it like another like the Dunham Bush one. You do it based off of the sight glass. There's a sight glass in that eductor return line, and we've got to tune that valve based off of that sight glass once the machine is in full operation and we've got the liquid level calibrated into the evaporator and all that's set up. Um, and train in the same way, like their reference is just, for example, I've seen these filters will be frozen solid blocks at times, and like they'll be really cold. These shouldn't freeze or have excessive sweating and stuff on them. And what I find is usually that's because this valve is open too far, and you choke this down a little bit, and these won't do that. And it goes back to you just that's a lot of factors dictate how much flow goes through here. The level of the machine has a huge impact in there, and even just slight elevation differences between one end of the chiller to the other, and it's not perfectly set, like perfectly level. Well, that has a big impact on where that refrigerant distributes and how it's going to interact with our eductor system. Um, so there's many factors at play that affect where that valve needs to be for proper flow on the eductor. Um, and when I've all the training I've had on this goes back to you've either got a sight glass or you've got other symptoms like, you know, your temperature and pressure in the tank, and if this is having issues, or if you're say like you're freezing up on your filter lines and stuff here, then you're sending a little bit too much liquid through there, and it's not you need to back this down to send it a little less so it's not able to freeze like that. That's one of the symptoms. Stuff like that. All right. So that's your basic. Oh, go ahead. Go ahead. Yes. Yeah, you could think of it like that. Absolutely. It's about the total volume moving through there. So like on that Dunham Bush, as an example, when we calibrate that valve on the Dunham, uh, you're watching your sight glass and you want to see it flashing. And when you get a stable evaporator and everything's smoothed out and you go to calibrate that oil return valve, um, if you see a full column of liquid in there, then you're too far open, and it's not okay. You'll end up sending too much liquid through there. You want to tune it in to where it's got a really heavy mixture, and you want to see it flashing very heavily in there as it returns back. In terms of getting into the evaporator, yes, you could have additional debris, whether it be some dirt from, say, somebody opened up the system to work on it, or they got some metal shavings from a pipe, or whatever happens, that material could be floating in that refrigerant. It could get drawn into the line. So having a filtered a dryer there that, um, yeah, sure, it's going to help account for any moisture caught in the system, but also just being a literal like filter for heavy material. Yes, that would be one of the functions it could serve. 'Cause this is also, like, this is things that have happened with like our oil pumps. So if you go if you go do an overhaul or tear down on, say, a centrifugal, and these trains, they want you to use 515 on the gasket flanges to seal it back. Well, one of the issues with 515 is it's known to harden uh, really bad, and it doesn't stay soft and tacky like, say, a 554 would. Now 554 will still harden a little bit. It's not like nylog that will stay at a fluid state. But either way, stuff that has happened is when that 515 hardens and then it makes it back into the oil sump, that little piece of hardened 515 will make it up into our oil pump, and it'll lock that gear pump up, and it just can't rotate at that point. And the only way to fix it is to take the machine or to pull this sump assembly out and open the pump up, and and see, does it have any debris in there. And that's one of the things, like, so if you recently did an overhaul and the pump was working fine prior to the overhaul, and then suddenly it just up and stops one day without any warning, like, it wasn't having any symptoms outside of, it wasn't having any symptoms, and then all of a sudden it just stops and it won't spin over. um, that's one of the first things you really want to check. It's probably not a bad pump necessarily. You probably got a piece of debris that pulled up in there and it's got that pump locked up. Hopefully you haven't tore anything up in the process, and you can just pull that debris out of there, seal it, put it all back together, seal it up, and then you're back online. Any other questions around that? All right, let's move into a YK example. Now, these can be done a couple of different ways. So, on your specifically your larger systems, I see this implemented where you'll have um, your tank will be lower down and it'll be mounted underneath, and uh, the eductor system will be external. It won't be internal to the tank. And some of the newer and or smaller YKs, the eductor block will actually be mounted inside of the tank itself. And so on the back of the oil sump, you'll have your hot gas line, which is right here. So it's coming off of a valve. It'll just come directly into the eductor block. And then your other lines, so you have another um, you have another oil drain line coming off the nose cone of the compressor, so that'll draw off just like the CVH. And then this valve could be a little misleading. It almost looks like this is coming off of the bottom of the evaporator. This is actually, I'm sorry, coming off the bottom of the condenser. This is actually a valve on the evaporator that's about mid-level. So this one should be, probably a hybrid falling film. Either way, this is your low pressure liquid refrigerant line coming off of the evaporator right here, and that's interjecting into this eductor block, and we can control that via this solenoid valve. So this solenoid valve is, we're able to manage when we want this eductor assembly engaged or not. Where in a lot of our other examples, if the chiller is online, the eductor system is functioning. With the YKs, we actually um, control when this engages or not based off of startup shutdown and what our conditions are at the time. Uh, Either way, we have a hot gas line coming in, hits this block. Then we have our low pressure liquid coming through. We also have a filter dryer on these. These filter dryers on this particular machine are meant to be serviced semi-annually. So these are actually made to where this solenoid can close and isolate, and you can isolate a service valve down here on the evaporator, and we'll isolate this particular part of the system. And then you can remove this filter dryer. It should be a flare style, and then change it out, and then open your system back up and get it going again. So these are meant to be serviced. Now, not everybody takes the time to service these filters like they're technically supposed to, but if you follow things by the book, that's what they're going to tell you. Either way, this is just the YK's example. We've got our medium pressure oil latent line coming back into here and hitting our block. We also have a vapor vent line coming off of the oil sump that does return up to our suction and hits the side of the compressor up here so that we're able to vent. This line here, this is not a vent, this is a drain to allow the oil that gets into our scroll or our rotor assembly where the gears and stuff are, allows it to drain down and into our sump. So that's what this pipe here is doing. But we also have a separate vent line just like we did with the train, except it goes up into the compressor, whereas the train style return to the evaporator, at least on the newer machines. So overall, same basic science, same basic flow, structure, all the same things are happening. We're just applying it in a slightly different application. And again, with these Yorks, it could be an external eductor block, it could be an internal eductor block. If it is eternal, it'll be mounted at the very back of the block, furthest away from where the end cap is, and it'll be right next to where the oil heater typically inserts. And so, yeah, this is just York's way of doing the same basic thing. But those are your overall flavors of how each manufacturer is able to get that oil recovery process. Now, I did mention that the Train RTHD had a little bit of a different process to it. So essentially with that one, just to explain it here, it's got 4 lines attached. It's got a evaporator drain. It's got an evaporator vent. Then it's got a high pressure high pressure gas line coming off the condenser coming into it, and then it's got a output line that goes back up to an inlet port on the compressor itself. So there's 4 lines total, and 3 of them have solenoids, or all 4 of them. I forget which. Either way, part of what Train is doing there is during the recovery cycle, and this is all timed, so it's all based off of time. That little canister at the bottom of the evaporator, they'll open the drain line and they'll open the vent line to the evaporator, and that will allow because the evaporator vent line goes up to a higher point on the evaporator to where it's just vapor, and that allows that liquid at the bottom of the evaporator to drain into the gas pump chamber. And then after a certain period of time, we expect that so much refrigerant's gotten into that point, and we want it to be oil latent so we can get that refrigerant back. And this is a screw machine, by the way, if you didn't know. So then when it comes time to get that oil to return, we will close off um, the drain line and the vent line, and then we will open a hot gas line from the condenser and use that to physically push the oil latent liquid refrigerant back up into the return line up into our compressor. And there's an actual orifice up there that helps us uh, pressure reduce that down and flash that liquid off, so it doesn't stay in the liquid form. But we were able to get the oil up at that point and get all that to return to the compressor, and then from there the compressor recycles it into the refrigerant stream and sends it through some oil separators, and it drains back out into the sump, and cycle goes back around and around. So just as another example of, instead of implementing an eductor block, they're using what they call a gas pump. And it's called a gas pump because, well, that liquid drains down and we're using discharged gas to then push or pump that that oil latent refrigerant back up into our compressor to recover it. That's the high level details there on that particular setup. So yeah, these are your oil recovery systems, with falling film and flooded evaporators. And because of our overall design, we're not able to maintain the velocity required, nor do we really want to in most of these cases, to get that oil back up into our compressor to cycle it around. So we have to implement these recovery systems in order to get that oil back and get it into our sump area, so that we can then circulate it back around and make sure that we're not stacking. Because the if you're having issues with, say, saturation problems, and you have really high approach values, it very well could be an oil stacking issue, or your oil may have migrated, something like that. So one of the ways that this happens is, during shutdown, especially if you say got like a pony chiller, or you're running you're running multiple chillers at a time, or you've got redundancy in your chillers. You need to isolate that chill water flow, and you should have an isolation valve on that evaporator to isolate it, so that you're not flowing cold water through that evaporator during the off cycle. Because what'll happen is that cold evaporator will begin to migrate that oil out of your sump and into the evaporator. And this is something where actually it was an RTHD I was having this issue with. The isolation valve had failed, and it wouldn't fully seal off and close. And it was allowing just a small trickle of chill water through that evaporator with the other chillers in the plant online. Well, that was enough to where if that chiller was allowed to sit like that for 12 to 24 hours, then the next time it went to start, it would trip on oil loss, and the little peep sight sensor in the reservoir would show that we lost oil. So in a situation like that, the way we were able to correct it, well, one, the valve needed to be replaced, but two, to get it back online, the simplest option was we would usually put about 1 to 2 gallons into the reservoir. That was enough to allow it to start up and get online and start to circulate again. And then, as the oil had time to get recovered via the gas pump, we eventually would then go back and pull that oil back out that we added, because it wasn't that it was low on oil, it had just migrated out. So in a situation like that, sometimes that is the easiest solution. Uh, just add some oil temporarily back to the system, let the recovery process happen the way it needs to, and then as you start running high oil levels again, start drawing that oil back off, so that you can return to a normal level and condition. And just, you should know how much you added in, so you should know how much you need to take back out. Should be pretty straightforward. Um, anyway, oil recovery process and systems for chillers. Questions? Yes. So, I mean, we use pressure differential for a lot. I mean, most everything we do in these systems, whether it be refrigerant or oil based. And I mean, you want to go to a screw. Most of your screw compressors on the market, they don't have oil pumps. Everything is differential based. That's why it's really critical that a screw establish pressure differential very quickly upon startup, um, so that we can get in. Without differential, we can't move oil on most systems. So yeah, just yes, we're using pressure differential to create and in some ways regulate our flow through these systems without having mechanical, like a there's not a oil recovery pump necessarily, like a mechanical pump happening. It's just using the pressures in the system to accomplish the task. Mhm. Yeah, there's ways to do it, but you're adding cost, you're adding complexity, and uh, you're reducing efficiency because something has to drive that pump. So now we're using more electricity in the end, and it's just not necessary. Now, in terms of, yeah, you could get like a gear style pump that can manage um, the liquid moving through it, and then if you regulate the pressure properly, then you could get the flashing that you needed, um, without having to do anything fancy. And so yeah, you could mechanically do this if you wanted to, but it's just we don't need to, and we can improve reliability and efficiency by not doing it mechanically, but allowing our pressures we already have at our disposal to do it for us via, eductor. They all use water temperature for capacity control. The liquid level sensors, whether it be on the condenser or the evaporator, are there to control the metering device specifically. So we control the metering device based off of heat exchanger liquid level, either way you go with it. So York is using the condenser level. Other machines like RTHD by Train or the um, uh, AVX by Dunham Bush, those are using evaporator liquid level, and then we modulate the metering valves based off of that level. Uh, but the compressor gets controlled based off of leaving water. So as we need to cool the machine down, or as we need to cool the water down more, the compressor will ramp up, and then that will influence where our levels are in the heat exchangers, and then the metering valves will adjust accordingly to get that level back to whatever set point it was meant to be at, which is overall how we balance the machine and we're able to maintain a stable level and flow during operation instead of trying to rely strictly on, say, superheats, which are very subjective. Yeah, again, it comes back to instead of controlling based off of superheat, whether it be discharge superheat or suction superheat, because there are plenty of machines that control their metering valves based off of discharge superheat, not suction. Um, so if we're not going to do it that way, then we can do it based off of our level sensor. Yeah. So it's just another way of doing the same thing. And if we maintain X amount of level in the heat exchanger, then you know, all things considered, we should be controlling our superheats properly as well. Because if we run too high of a level, we lower superheat. Too low of a level, we have a high superheat. Direct correlation. Any other questions? Yeah, no, I mean this is it. This is how we're using eductors. This is how we process oil recovery inside of a chiller, whether it be air cooled, water cooled, screw, centrifugal. Um, you don't see this kind of stuff with, say, reciprocating or scrolls because we don't typically use these types of evaporators with those. So, yeah, just with a screw or a centrifugal, we use the evaporators that um, need these recovery systems in place for it to function properly. Either way, I appreciate it. Enjoyed the time, enjoyed the chat, and I'll see you later.